Okay, hello everyone. Welcome back to SFC's first ever Student Research Festival. We're hosting 3 graduate or upper year undergraduate students this week to share their cutting edge research in natural resources. This festival is an opportunity for students to share their knowledge in a friendly, low pressure environment with other students. This is our first research event, but we hope to host more. So please follow SFC on social media at Students for Canada on Instagram, LinkedIn, and Facebook to hear more about our future events. For those of you who are just seeing SFC for the first time, we are an advocacy group made by students and young professionals for students and young professionals who believe that Canada can have a strong future in resources, the economy, and the environment. We are very fortunate to have such fantastic support from a variety of students and young professionals, Dylan included. Today's festival presentation stars Dylan Hematillake. Dylan is an engineer in training and a data scientist at Suncor Energy under the In-Situ and E&P business unit. His focus is on the development and implementation of explainable digital technologies to improve upstream operations through reduced operational expenses and greenhouse gas emissions. He graduated from the University of Waterloo with an honors Bachelor of Applied Science in Chemical Engineering with a specialization in material and manufacturing processes, and is currently pursuing a Master of Science in Computer Science from the Georgia Institute of Technology with a specialization in machine learning. Before I hand the floor over to Dylan, please know that attendees are encouraged to ask questions throughout the presentation using the Q&A box below, which you can do anonymously if you're more comfortable with that. We will address all of those questions at the end of the session. I will now share our spotlight with the first speaker of the week. Welcome, Dylan. We are so excited to hear more about what you do.
So Industry 4.0, it's kind of a big buzzword that's thrown around quite a bit. And a lot of people are wondering, what about Industry 1.0 or 3.0? These are basically the major industrial revolutions, the first being the steam engine and steam power and mechanization. Then, of course, the world wars occurred and we needed to have increased throughput and development. From there, after that, we started working on electronics, automation, trying to optimize layouts and maximize the ability to generate profits. 4.0 is the next step in industrial revolution, and it's the idea of things like IoT, desilicification of structures, and leveraging interconnectedness of digital technologies. So you hear concepts like smart factories, smart machines, and these use high volumes of data to inform decisions about themselves and the processes that they're part of. We can optimize, we can integrate and improve maintenance through predictive methods. We can synergize organizations in ways we haven't been able to before, and augment different aspects of the workflow. So the idea of augmented reality for plants, where an inspector can walk through a plant digitally and then suddenly see a part's wrong, order it instantly, get that replaced, all from the comfort of his home or her home. So Industry 4.0 is poised to maximize the value of what we have in terms of information, remove inefficiencies in this complex network of today's processes. Another important aspect of Industry 4.0 is the idea of the connected worker. So as we've seen over the course of the COVID-19 pandemic, for example, employees don't really want to settle for the typical 9-to-5 structure, right? We realize people have diverse interests. They want to have work-life balance, broad compensation packages. And at the same time, natural resource companies are facing increasing pressure to be more accountable, especially to environment, sustainability, governance principles, ESG. There are 3 major approaches that companies often take when it comes to the environment part, which is divestment and diversification. For energy companies, this usually means adding renewables to the mix, translating current supply chain to lower carbon intensity products, technological developments that can reduce emissions in current processes, as well as optimization of current processes. The last is what's more considered the easier win for resource companies, and digital technologies are empowering them to do so. So through implementing smart models, we can monitor and optimize these processes, which have a low capital investment usually, but have great gains in terms of OpEx. The last kind of preface I have is machine learning methods. So these are very specific aspects of the whole digitalization toolbox that we can use to leverage information and data fully. So there's a lot of information that resource companies have, financial companies, all of them, and it's not really leveraged to the maximum potential. And that's because of difficulty of scale, difficulty of accessibility, and structure. Machine learning is a specific aspect that allows us to maximize information gain. We can enable really good ease of experimentation. We can iterate quickly, and that's because a lot of machine learning has been compressed into open source repositories and software that's been developed throughout the years. Machine learning, you'll hear, is often considered part of artificial intelligence. It really depends on how you're leveraging it, because artificial intelligence you can think of as trying to build agents or things that can take on the task or the role a person may do. Machine learning is one way that an agent can learn this, but machine learning itself is just the model. You need to actually do something with it for it to be an artificial intelligence agent. But it's important to consider this because we can empower workers to spend less time on monotonous, more repetitive work and focus their talents on other aspects. So with that kind of preface, I'm going to jump into what the research project is, and it's a very specific application of machine learning. So my group, we researched this application of deep learning for certain unit operations. For those who aren't familiar with that, unit operations are essentially blocks in a process that manipulate product flow in some way. In this example, you'll see this continuous stir tank reactor here. So there's a bunch of things that go in and the product that comes out. There are many different levers we can play with to control and optimize that production. The problem is with that bulk of information, it's often quite difficult to analyze and optimize on the fly to have the controls at the best possible setting, such that we're actually maximizing profit. So this is one kind of area where companies are investing quite a bit in terms of 4.0 is the idea of design optimization, monitoring, and then fault detection and diagnosis. So if something's going wrong, we need to know it's going wrong, and then what's specifically going wrong. This allows us to mitigate losses and then quickly replace or adjust components as needed. Now, what is the general problem that we wanted to investigate? An important part of the loop is that we consider a design of a reactor or a component independent of the monitoring technique, generally speaking. But the assumption of independence isn't necessarily true in that one informs the other. So you may build a design that could theoretically maximize production, but that design may end up with a terrible monitoring model. So if you fold them together, you can actually maximize profitability in ways that you couldn't if you considered the design of a reactor independent of the fault detection model. So in the research, we proposed essentially a folded method where we have the design hand in hand with a process model that's also able to classify and identify faults and issues that occur in the process. We bring that together to form the optimization space where we have the design and the accuracy and performance of a model and maximize the total profit. The methodology is quite simple. So in this application, it was a penicillin bioreactor process. And in bioprocesses, it's fairly limited in terms of runs and the incidence rates of different faults. So there are a lot of different things that can go wrong, but maybe it'll be once every 100 or 1,000 batches. And those 1,000 batches would be over 10 years, right? It's very expensive to also have simulated in an actual pilot plant. So we ran to this industrial simulator from a partner. And so with that, we generate different faults throughout this process. We then compare to a benchmark model, which is a PLSDA model. We build a deep learning approach, and then with those two models, we have the optimization of our design, and we find what works best. Now, in terms of faults, for those who aren't familiar, and in terms of this context, a fault essentially is a mode of operation that's unexpected or leads to impacted profitability. In the specific experiment, there are a number of different faults that can occur, from actual aeration, pressure, rates, and sensor drift. So all of these have different levels of complexity and how they impact the process, as well as how hard they are to detect. So sensor drift is a common problem in industry, especially upstream. And it's not always easy to catch because it slowly changes through time, and it's also can oscillate differently in terms of the process control. Let's see. Now for the benchmark model, what you see here is called PLSDA, and essentially it's a multivariate regression. So you have your input here. This could be temperature, pressure, flow rates, power demand, etc. And based off of those different signal combinations, there is an output class. So you can consider one class to be operating normally. Another class could be underheating, right? And so based off of the training testing data, you have these curves that are generated from the multivariate regression, and you set a threshold. That threshold basically decides what class it belongs to. And that's similar to how you get classification out of, say, logistic regression. A logistic regression is a probability output, and you slice it basically at a certain probability to say it belongs to class A, B, or C. Now for the deep learning aspect, for those who aren't familiar, deep learning essentially uses these things called neural networks, and they have layers in between an input and an output. The number of layers that you have essentially is what dictates the deep part, because more layers makes it deeper. Neural networks are composed of interconnected layers. They're made up of these little things, neurons. So they take the inputs, they map them in a linear transformation, and then they throw this into a function called the activation function. This is a nonlinear function, and these chain together to actually be able to capture a lot of the complexities in data that aren't as straightforward to investigate. So when you have not just one layer, but 3 layers, and you have hundreds and hundreds of these neurons together, you get a chain effect, which allows for universal classification that you can't get necessarily through simpler models. The structure that we proposed in this research is called a supervised convolutional autoencoder. And so there is an encoding part and a decoding part. What happens is we take the process as it occurs and we compress it down to a representation that is the bare minimum kind of signature of a process. So there's a unique signature for a good operating batch. There's a unique signature for something that's gone awry. We can then build a classification layer in there to identify those different faults, and then a decoding component, which then has a representation of the process. So we can model the process at the same time, classify different things that occur. For the design optimization, what we looked at were several key characteristics of the reactor that had a big impact to production. So in this case, there's the impeller speed, the impeller radius, the surface area of cooling coils, feed concentrations, and so forth. And we set them to different levels. So 0 represents the base configuration, and then -1 and 1 are slight changes. This allows us to do what's called a response surface optimization. So we create a surface based off of this, and then on the characteristics of that design, can then do different analysis to determine where the maxima is. So in terms of model performance, what you see here are 2 different confusion matrices. Now, if you aren't familiar with what that is, it's a method we can use to see how classifiers are performing. Here is the actual fault, and then here is the predicted from the model. This is our benchmark, and then this is our deep learning model. Ideally, you'd want along that diagonal to have ones across the board. That means you have a perfect performing classifier. As things sort of get confused, essentially you have cross-correlation between features. You could investigate why that is, but you want it to align perfectly in the diagonal. And so we can see here that our deep learning approach is greatly incremental to the benchmark standard that the company was using. So we look at that base configuration, and now we look at all the different design possibilities. So that is essentially factorial of 6 factorial, and then it's spaced differently because of the design of experiments to make it more efficient, because there's repeated designs across that. So there were 79 different configurations of that reactor. And so across the board, we can see that the deep learning model performed quite well in comparison to that benchmark that the company uses. So about a 25% or so increase. Then we take that performance, those configurations, and those are all inputs to our response surface. We take that, build the regression, and then we can optimize on that surface. Based off of that, we get these design parameters. So these are the best possible ways to design the reactor to maximize profit. For the benchmark fault detection model, we get a profit of about 3,200 kilogram per batch. You multiply that by your margin, and then you get a dollar per batch value. But the convolutional neural network has a different configuration design, but also a much greater profit. So we can see that the designs are different. They're not the same design. And because we folded in that monitoring consideration into that optimization, we get quite a different yield. So some conclusions on that is that our proposed deep learning model properly folds in that integrated process monitoring design approach and allows for sustainable and more economic design. You aren't going to be worrying about the drift of your models, or you build this whole reactor and do this investment, suddenly you can't actually monitor the process as well as you could have. And so by implementing better FDD models, we can reduce process upsets, we can maximize value of the resources we're developing, and furthermore, we can reduce exposure and enable people to work better. So if we can diagnose and proactively maintain our processes, it reduces a lot of hazards that come just from exposure hours. And then of course, in this experiment, we got about 25% increase to profit in this penicillin batch reactor. If you want to take this approach and apply it to other unit operations, you can do a transfer learning approach, which means you take kind of the configuration we have, you feed in a couple extra data points and see how that adapts. For those who are curious, this is the reference paper. And yeah, I'll take questions.
Let's defer to our resident engineers first. So Jessica, do you have a question?
Yeah, I just want to know is what is the most common fault that occurs that you have to deal with?
That's a good question. My day-to-day work, it's often issues with instrumentation and the valves. So thermocouples are really finicky, pressure gauges are really finicky. Valves have a lot of reliability in them, but there's often degradation that occurs. So those are main pain points. It's usually not the overall unit operation that's the problem. So
Thanks so much for your presentation, Dylan. I was wondering if there would be external faults that could occur from like outside changes, like if your batch reactor was outside, would the environment change your temperature, and would that just be another fault, or would that change existing faults that you've considered?
yeah, so ambient temperature is a big kind of factor for things. Humidity is an important factor. Theoretically, you treat a lot of these as closed loop controls. And so effectively, you're trying to control against your environment with your inputs. So your input cooling, your flow rates, your pH meters, etc. But they do have an impact. In terms of the fault detection monitoring, it doesn't, because it would automatically consider that through the interaction of the other variables. But it's an important variable that is often neglected. One example is we have cogens at work, and a lot of those are affected strongly by ambient conditions. So we can get a lot more power out in the winter because it's colder and density is different, versus in the summer we have to make up for losses here and there. So it's definitely an important factor that's considered. Yeah, exactly.
So when going from the one process to the deep learning process, I noticed that the aeration, I think it was on slide 16, the aeration actually goes down in percentage, whereas everything else goes up. So I was wondering if you could explain that.
Yeah, and that has to do more with the complexity of faults. So an aeration fault is a very linear fault. It's very obvious. Like if you looked at a graph of aeration rate versus time and when the fault's introduced, it's a very notable difference, right? So the model, the PLSDA model, works really well against linear faults versus the deep learning approach tries to generalize as much as possible and learn all the interaction effects. So it's really good as a nonlinear classifier. technically you could train a deep learning model to the point where it's like 100% perfect, but then you have the risk of overtraining it and then it generalizes a little poorer. So we took a little bit of the generalized approach because we want it to work in many different cases, many different faults. But if you only have really linear faults, it's best to do the simple thing and go with the benchmark. You can even go simpler sometimes with SVC control, just simple standard deviation bands on those really linear faults, and you're probably good to go.
Excellent, thank you.
Yeah.
Jessica, did you have another question?
Yeah, so it looks like here in our Q&A, we have a question. It looked like your project focused on pharmaceutical products / industries. Could you apply the methodology your team researched to other processes and industries?
Yeah, so in this case, it was pharmaceuticals, but it generally applies to anything, right? So let's say you have a distillation tower, you have your cooling flow rates, you have your products outflow, you have your inputs. It's all just about what variables you go in and how you want to train it. It's not a matter of it being hyper focused on one industry or the other. So all unit ops basically work the same. You have inputs, outputs, controls for equilibrium, and those are levers that you can play with to change production or affect the way that you're operating. So it works for quite about anything, and it's worth studying in other applications.
Good to know for sure. We have somebody in the Q&A says, I wish you would have taught my unit ops class. Lol, you should be a prof. So maybe Dylan, if Suncor doesn't work out for you, you can be an academic.
Yeah, maybe.
Awesome. Okay, so just a few like personal questions because you are our graduate student in this event. And I know we have some people who are kind of curious about, the processes and programs and stuff available. So what made you choose your program at the school you attend? What's some advice you might have for folks who are looking to do something similar?
Yeah, so the program I chose, the reason is that it's part-time and it's online, and it's a pretty good program in general. I wanted to keep working and then do this kind of on the side to supplement my work, extra challenge, I suppose, and learning, networking, so forth. But I guess it depends on your goals and what you want to do, where you see yourself. I'm in R&D technically, and so we work from ideation of different digital technologies all the way to the deployment to the plants or to the assets. So for me, it's worth learning a lot of the intuition of the different models that we're developing. But a lot of experience is best had in the plant, especially if you're focused as an engineer. Like everything's very different, even if you have very similar equipment. You have same turbines, distillation tower, separation drums. Like everything's very different plant to plant. So it's worth going out and getting that experience. If you're looking to pursue graduate studies for the sake of just getting a job, you may need to consider how that ties into your career plan. But it's definitely worth pursuing that level of education, just focusing on something or getting more exposure to different subjects. So I'm doing my graduate degree in computer science, and that's because it kind of ties into my work. It's something I'm really interested in. And it's supplemental to my undergraduate in chemical engineering with that process control kind of background. So my advice is, well, if you're looking to get a part-time job, I guess, or you're full-time, to see if your employer would cover some aspect of that and what reasons they would have to. So how is it improving you as an employee or you in terms of your interests? But if you just want to do it, I'd say just go for it. And there's a lot of programs out there. They range from full research all the way to just course-based. And depending on where you go, if it's in Canada, in the States, or out to Europe, there's different structures to those. So
Yeah, that's a really great point. I'm also doing a master's right now in political science, and it's just an extra opportunity to get really into something passionate and to continue to kind of like grow one's toolbox and meet new people. Um, what excites you about your future and resources? Like, what do you think the industry is changing that's really interesting for young people?
yeah, I think a lot of the industry is seeing that young people need to be enticed back into it. So that can come in a different set of outcomes. So there is more flexibility to the work. There's more diversity in what you can do. There's a lot of opportunities in the digital space, a lot of more opportunities in the engineering space. So it's hard to keep people who want to work in the plants now as engineers. And so there's a lot of adaptations to work-life balance that weren't there before necessarily, and a lot of enrichment opportunities that are there. So those are things that they're continuously offering. Um, and so as other fields are kind of competing for young people, they're trying to target what exactly it is that young people want. So I think that really does come down to work-life balance, better compensation, and then just like feeling like you're actually making an impact at your work.
That's a great point for sure, and that's what we're hearing too is industries really are competing for young people. So, finally the odds are in our favor.
Yeah.
Um, our final question, unless we have somebody in the Q&A. In creating an in-depth research project like this one, what are some first steps or your tips or advice that you would recommend to someone who wants to start something similar?
Yeah, so if you're in school still, I definitely recommend finding a mentor or supervisor. So professors are always looking for someone to help out with research. It takes a while to get familiar with a field that you're interested in to actually start a project from scratch and then carry it out. I mean, that's what PhDs are meant to train you on. So definitely finding someone who can guide you through the process. So I had a professor help me with this project, and he supervised the design project with my team. And then we had our industry sponsor, so he had the insights for what made sense in terms of the context of industry applications. So that marriage of academia with industry is important for a design project. So in terms of research, there's always industry research that's always posted around, so maybe worth looking into if your university works with partners. And then if you want to go towards the pure academic side, your professors definitely always have like a project. If you're outside of school now and you're working, it's definitely something you need to fish with your supervisor, your manager, what new technologies in development or what areas of research that you're interested in that are potentially open for investigation.
That's a great point. It definitely comes down to who you know and, whether or not they can see like your work ethic and your drive to do something bigger. I guess we'll end on our last question here. What is your hope for the resource sector?
My hope for the resource sector, it's a big question. Um, I guess my hope is that we can transfer to a smarter way of operating. I think the culture itself is going through a bit of a change, and that requires good change management from organizations. So they need to really adapt with the evolving expectations from external pressures, so ESG especially. But I see that they're doing that, and they're moving towards a cleaner way of operating. And as that occurs, there's always these new opportunities that evolve, technologies that evolve, and I hope that they'll continue to grow and expand on that, and then continue to enrich people's lives. So
Yeah, that's a great answer for sure. It's the old saying pressure makes diamonds or whatever. I'm
yeah,
not the engineer, but that's what I've heard. Okay. Well, I believe that about wraps us up for today. We're at 5:32 p.m. my time, 3:32 your time. Dylan, thank you so much for your time and your willingness to share. We really, really appreciate this.
yeah, no, perfect. Thanks for having me.